We now start our discussion on chapter 5. In this chapter, we will consider the notion of Lebesgue integration. You already are familiar with one integration process, that is Riemann integration. Just recall that if f(x) is a bounded function defined on closed interval a b, then integral a to b f(x) dx determines the area between the curve y is equal to f(x), the x axis, and two vertical lines x is equal to a and x is equal to b. And how we calculate that area? We take a partition P of closed interval a b and then construct the corresponding upper and lower sum of the function f corresponding to this partition, which are denoted by UPF and LPF. So, in general, this number UPF denotes the sum of finite number of rectangles, their areas, which are above the curve y is equal to f(x), and LPF denotes the sum of the areas of finite number of rectangles which are under the curve y is equal to f(x). And we take more and more points inside the partition P, so that the upper sum decreases and the lower sum increases, and the Riemann integral or the area of that under graph is obtained as the limiting value of both the upper sum and lower sum. Now, the problem with the Riemann integration is that it cannot deal with functions which are badly discontinuous. For example, consider the function chi q defined on closed interval 0 1. Now, if you think about the graph of chi q, the graph consists of countable number of vertical lines. Now, it is easy from our intuition that we cannot make an area or region with positive area with the help of only countable number of vertical lines. We need at least uncountable number of lines. So, this particular function chi q, this is actually only a simple function, we already know it. It is not that a bad function in terms of measure theory, but we cannot integrate it. So, we will try to develop a new integration process which will be modified from the Riemann integration, so that the weaknesses of Riemann integration is overcome. We start the presentation for module 1 of chapter 5. So, recall the definition of Riemann integral again. We take a partition P, a is equal to x0 less than x1 less than x2 less than xn is equal to b of closed interval a b, and construct the upper and lower sums as UPF is equal to sigma I is equal to 1 to n capital M I into xi minus 1. This is the upper sum of f corresponding to the partition P, and LPF is equal to sigma I is equal to 1 to n small m I into xi minus 1. This is the lower sum of the function f corresponding to the partition P, where capital M I stands for the supremum value of f(x) in the interval xi minus 1 to xi, and small m I stands for the infimum of f(x) over the interval xi minus 1 to xi. We define the lower and upper Riemann integrals. Also, these are actually called Darboux integrals as follows. The lower integral a to b f x dx is defined as the supremum of all possible lower sums, where the partition P runs over collection of all partitions of closed interval a b pi a b, and the upper integral a to b f x dx is defined as the infimum of all possible UPF, where P runs over pi a b. Pi a b stands for the collection of all partitions of closed interval a b. And we say that f is Riemann or Darboux integrable on closed interval a b if the lower integral a to b f x dx is equal to upper integral a to b f x dx. Consider this definition. A function phi from closed interval a b to r is called a step function if there is a finite collection of pairwise disjoint open intervals I k, where k runs from 1 to n. So, there are n number of intervals such that phi is constant on each I k, and union of the closures of these subintervals, that is I k bar, their union. So, union k is equal to 1 to n I k bar, this is the full interval closed interval a b. If the step function takes the value c k on I k, then one can see that phi can be represented in the form phi is equal to sigma k is equal to 1 to n c k chi e k, that is the characteristic function of I k. Of course, here we ignore the value of phi at finite number of points, and actually this does not harm anything, because the value of phi at finite number of points does not affect the value of the integral of phi or the integrability of phi. And we define integral a to b phi x dx as the sum sigma k is equal to 1 to n c k into length of I k, where L I k stands for the length of the interval I k. So, suppose f is a bounded function defined on closed interval a b. Now, see that the upper sum and lower sum which we had constructed already, they can actually be thought as integrals of step functions which are above the function f and which are below the function f. So, the upper and lower Riemann integrals of f on closed interval a b can be defined in this way, that upper integral a to b f x dx is equal to infimum integral a to b phi x dx, where phi is a step function and phi is greater or equal to f, and the lower integral a to b f x dx can be defined as supremum of all integrals a to b psi x dx, where psi is a step function and psi is less or equal to f. So, these are alternative definitions of the upper and lower Riemann integrals with the help of step functions. Recall that in chapter 3 we had considered step functions and then extended the notion of step function into simple functions by just taking measurable sets instead of intervals. So, we will do the same thing while developing this new integration process. So, just think that while defining the Riemann integration, what we did is that actually we defined the Riemann integral of step functions, and with the help of the integrals of step functions, we have actually defined the Riemann integrability as well as the Riemann integral of bounded functions. So, here we will consider measurable functions, and since we already know that simple functions are the simplest form of measurable functions, so we will start with defining the Lebesgue integral of simple functions. And now we go to our next slide. So, we start again with the basic definition of simple function. Suppose S from E to R is a simple function where E is a measurable set and the measure of E is finite. Suppose S takes the values alpha 1, alpha 2, alpha n on E, so that the canonical representation of S is given by S is equal to sigma k is equal to 1 to n alpha k chi E k. Then we define the Lebesgue integral of S on E as integral over E S d mu is equal to sigma k is equal to 1 to n alpha k mu of E k. So, see that while defining the Riemann integral of step functions, we had taken the lengths of the subintervals. So, just we have replaced the intervals by measurable sets and replaced the lengths of the intervals by more extended notion of Lebesgue measure of the measurable sets. We first observe some basic properties of the integrals of simple functions. Suppose S and T are two simple functions defined on a measurable set E of finite Lebesgue measure, then 1. For any real number C, integral over E C s d mu is equal to C into integral over E s d mu. 2. Integral over E of the function s plus t. Note that if s and t are two simple functions, then s plus t is also a simple function. So, integral over E s plus t d mu is equal to integral over E s d mu plus integral over E t d mu. Third, if S and T are simple functions such that S is less or equal to T almost everywhere, which means that outside a set of measure 0, S is less or equal to T, then integral S d mu over E is less or equal to integral T d mu over E. Fourth, same type of property, that if S is equal to T almost everywhere, then integral over S d mu is equal to integral T d mu. We continue theorem 1. So, again S and T are two simple functions defined on a measurable set E of finite Lebesgue measure. Then the fifth property tells us that if A is subset of B, of course, A and B both are measurable with finite Lebesgue measure, then the integral of S over A is less or equal to integral of S over B. The sixth property tells us that if A and B are two disjoint measurable sets, then integral of S over A union B can be obtained as the sum of the integrals of S over the sets A and the set B. And finally, this is also an easy observation that for a simple function S, the modulus of the value of the integral over E s d mu is less or equal to integral over E mod s d mu. We will only prove 2, all the other proofs are quite trivial and in any case are given in the course content. So, suppose alpha 1, alpha 2, alpha n are the n distinct values of the simple function S, while beta 1, beta 2, beta m are the m distinct values of the simple function T. Then we know that we can write S as a canonical representation in this way, that S equal to sigma I is equal to 1 to n alpha I chi E I, where as before E I is taken as the set of all those points x belonging to E, where S x is equal to alpha I, and T can be expressed in this form, that T is equal to sigma j is equal to 1 to m beta j chi f j, where f j is the set of all points x belonging to E, where T x takes the value beta j. Now, obviously, E I and F j, these are all measurable subsets of E. We take the intersection of E I and F j. So, let A I j equal to E I intersection F j. Then A I j is also measurable, and the collection of all measurable sets A I j, where I runs from 1 to n and j runs from 1 to m. These are obviously pairwise disjoint and their whole union is the set E, and on the set A I j, S plus T takes the value alpha I plus beta j. Then if we compute the integral of S plus T over the set E, then by definition this is equal to sigma over I and j integral of S plus T over A I j, because recall that the sets A I j are pairwise disjoint and their union is the set E. This is again equal to sigma sum taken over both the indices I and j, alpha I plus beta j mu A I j. I can divide this sum into two parts. So, this is equal to sigma I is equal to 1 to n alpha I, sigma j is equal to 1 to m mu A I j, plus sigma j is equal to 1 to m beta j into sigma I is equal to 1 to n mu A I j. Now, see that for a fixed I, the sets A I j form a partition of E I, and since they are mutually disjoint, So, by the additivity of Lebesgue measure, we have the sum sigma j is equal to 1 to m mu a I j is equal to mu e I. So, the first term becomes sigma I is equal to 1 to n alpha I mu e I, and with the same reasoning the second term becomes sigma j is equal to 1 to m beta j mu f j. And we know that the first term stands for the integral s d mu over E, and the second term stands for integral of t over E, and this completes the proof. Now, we start our main definition. So, let f be a bounded function defined on a measurable set E with finite Lebesgue measure. We define the upper and lower Lebesgue integrals of f on E by the upper integral of f over the set E d mu. This is defined as infimum of all possible integrals t d mu over E, where t is a simple function and t is greater or equal to f. And the lower Lebesgue integral of f over E is defined as the supremum of all integrals s d mu over E, where s is a simple function, but s is less or equal to f. And we say that f is Lebesgue integrable on E if the upper Lebesgue integral of f over E is equal to the lower Lebesgue integral of f over E. You can see the similarity between the definition of Riemann integral and Lebesgue integral. So, this definition is actually motivated from the definition of Riemann integral. But in the next presentation of the next module of this chapter, we will see that this new process of integration will be of much help to us. So, in this first module of chapter 5, what we did is that we have defined the Lebesgue integral of simple functions, and then with the help of the Lebesgue integral of simple functions, we have defined the Lebesgue integral of bounded functions over a set E of finite Lebesgue measure. So, we end this module here.